immediately start. So I'm going to share with you my thoughts on feedback-free starbursts at cosmic dawn. I'm going to ask you to do something very different from what we've done so far. Forget about everything you heard about yesterday and this morning, and try to play the little theory from first principles, okay? And then we go back to it. This is, by the way, a cartoon by Igor Novikov. So I'm going to tell you about feedback-free starbursts, the basic idea, and about how it's relevant to our universe at cosmic dawn, and then go back to observable predictions. I'm going to define star formation efficiency just this way, namely like Peter Beruzzi's m star over m halo, or according to the star formation rate and the accretion rate. And we all know that commonly we assume low efficiency due to feedback, on the order of 10%. The question is, what should it be at redshift 10 or above? Why should it be 10%? Or can it be a different story from first principles? I'm going to try to convince you that robustly, at high density and at low enough metallicity, for example, redshift 10, halos of 10 to the 11 solar mass, the star formation efficiency is of order unity, predicted to be. And that's what I call feedback-free starburst. The time scales, the characteristic, and the densities are coming from many different directions. They are on the order of 1 million year, 3,000 atoms per cc, and surface density of 3,000 solar mass per parsec squared. They all come in. The very basic, simple idea is from this diagram, showing you the mechanical energy from a burst of 10 to the 6 solar mass starburst as a function of time in million years. What you see in the dashed line is what happened to supernovae. Because of the lifetime of the massive stars, there is a gap of 3 million years between the burst and the onset of effective supernova feedback. That's the basic idea, that you have a window of opportunity of 3 million years. Well, you were asked about winds from stars. They should start right from the beginning of the burst. However, only if the metallicity is high, they are going to suppress star formation. If the metallicity is low, the metals have to be pushed out from the center of the star to the outskirts to make the opacity by dust for the winds to be effective. And that's another window of 2 billion years, provided that the metallicity is lower than, say, 20%, 10%, 5%, 1%. So we have this wonderful window of opportunity at low metallicity, a feedback delay of more than 1 million years after a starburst. Well, if the free fall time is shorter than that, then you can make all the star formation in whatever cluster is making the stars in a feedback-free way. Feedback-free in the sense of supernovae and stellar winds. That's the key idea. And as a function of density, time scale of 1 million years for the feedback, that's the window, and that's the free fall time. And you see that they cross at about 3,000 atoms per cc. That's the critical density coming in for the first time. And this is the regime of feedback-free starburst. Now you have to worry about many different things after this very trivial idea. And this is just a partial list that I'm going to address today very quickly, and then Kartik Sarkar is going to continue and elaborate. So I did discuss this, but we also have another enemy for star formation, radiative feedback. You have to make sure it's not going to be very strong. And Andrea Ferrara I'm sure will talk about this in his talk. You have to be cooling on a free-fall time scale to really make sure that you have to have a burst narrow enough, such as the gap between the burst and the onset of feedback will be meaningful. And then the cooling has to be more efficient than the free-fall time. You have to be shielded against supernova winds and UV radiation from earlier generations of star formation once you're talking about a given cluster trying to do an FFB formation. It has to be shielded against the others. And you also have to make sure that the cold streams penetrate efficiently through the halo to give you the high efficiency. So let me start with the radiative feedback. Just give you the result, which is very nicely analyzed by this paper. We may hear about this from Grudik. Simulations by Menon and Krumholtz really printed down very nicely that the radiative feedback is going to weak if the surface density is above a critical value on the order of few thousand solar mass per ASIC square. That's why surface density? Because forces go like surface density. And the case for no efficient radiative feedback is if gravity really captures and is stronger than the radiative pressure force. You also have to worry about other radiative feedbacks which apparently give similar results. So I just want to point out that this two-dimensional surface density relates to the three-dimensional density that we talked about before for the feedback-free star formation. Once the clouds that you talk about are on the order of 10 parsecs or more. In this case, no significant suppression of star formation rate by radiative feedback once the three-dimensional density is above the threshold to be in the window of FFB. Also, the radiative feedback is not going to be important. That's a nice coincidence. Now, cooling. The cooling time is in this regime where you have to worry about it. I just took some examples of molecular cooling, giving you this kind of expression. And it turns out that, again, the cooling time is below the free-fall time, above a very similar density. So there's some coincidence here, coming in from now a different direction, a very similar critical density of a few thousand atoms per cc, provided, of course, that the metallicity is not totally low. If it's zero, then there's no cooling. You cannot do this game. But if it's above 1%, between 1 and 20%, and that's not a big assumption to make, and can be confirmed, everything is going to work. So the cooling up. Sorry about that. So the cooling time, is this line here, goes like 1 over, and by some coincidence, it turns out that the same critical density is playing the game here. Well, within a factor of 2, all these numbers are the same. So it's not only the free-fall time below the feedback time, it's also the cooling time below the free-fall time in the same regime, defining for you the feedback-free regime. Now, what about shielding against earlier clusters that form? Now you're forming new clusters, maybe globular cluster size. You have to make sure that the wind that develops here is not going to crush this cloud before it makes stars. So typical crushing time is Kelvin-Helmholtz time. It's again a few million years, and you have to compare it to the free-fall time again. And it turns out that if the cloud mass is above 10 to the 4 solar masses, these clouds are going to be shielded. against this supernova wind from earlier generations of stars. And Kartik may elaborate on this. Also, one can compute UV radiation from these earlier generations, and it turns out to be unimportant in this new cloud, so they are shielded. In other words, if you have a 10 to the 6 solar mass cloud, this is the shielding upper limit. This regime that we were talking about for FFB is safe under this line. Now, for the real universe, what about massive galaxies at cosmic dawn? So first of all, let's make sure that cold gas goes in. Just to tell the numbers, the halo we are talking about, redshift 10, if it's 10 to the 11 solar mass or so, is about 10 kpc. The velocity of inflow is about 150 kilometers per second. The halo real time is on the order of 100 billion years. That's the time it takes the gas from the real radius to get into the cellular galaxy and form the whole galaxy. It's a much longer time than the feedback-free time. So the feedback-free cannot be monolithic. It has to be in clusters in many, many generations. The baryonic accretion rate is several tens solar masses per year, and if the efficiency is high, then this should be on the order of the star formation rates that you predict. The cooling, people probably remember this diagram when we computed the critical mass for shock heating at the real radius, now extended it to high redshift. The line is about here, and it turns out that the halos we are talking about, 10 to the 11 solar mass at redshift 10, are well below this shock heating, so we're in the cold flow regime where there is no real shock, no real hot CGN. So this is because the cooling now is atomic cooling, much more efficient than we talked about before. There's no real shock. We expect the cold streams to come in at 10 to the 4 degrees. The steam radius can be estimated in simulations or analytically to be on the order of a fraction of a kpc. That's important for analysis. So here's the big question. At what time and what mass of halo do we expect to be at the conditions for FFB? Here we have to apply to the morphology, and we use two extreme pictures. One in which the streams come in with no angular momentum, and the other one in which the streams come in with certain angular momentum and generate a disk rather than a shell, a spherical shell. So, radial streams, if you look at the function of redshift at halo mass for 5 sigma figs, 4 sigma figs, and 1 sigma pig, the galaxies we talk about at redshift 10 of 10 to the 11 solar mass halos from the abundance, they're about 5 sigma pigs. And such peaks are expected to have low angular momentum. You see how radial these inflowing streams are. On the other hand, we do see, in some cases, some angular momentum that lead to a disk. It will be lower than the angular momentum you expect at later times in massive galaxies, but still some significant spin parameter. Corentin, I guess you will talk about angular momentum and may touch this. So this is the second case, and so, sorry. So, in the case of radial streams, I want to ask, what is the density right here at the outskirts of the galaxy that starts forming stars? Can it be above the FFB critical density? So, clearly, this very highly supersonic stream of Mach number 15 is going to create a shock here at the boundary of the galaxy. Not at the real radius, but where the galaxy is, it must stop, it must shock. And since the cooling is still atomic cooling, very efficient, it's going to be an isothermal shock. In an isothermal shock, the density behind the shock is m squared times the density before the shock. And that's the key for this high density. You compute it with 15 Mach number, and you end up with the critical density that we really want for the FFB. That's the expected density behind the galactic shock that forms in this spherical configuration. Given a mass of 10 to the 11 solar mass halo and a redshift of order 10. That's the case of the streams, in the case of the shell, with radial streams. In the case of a disk, you simply use the contraction factor being whatever we assume for the spin parameter, 0.025, and we get the density in the disk to be lambda to the power of -3, that's the collapse factor, times some clumping factor, the star-forming region compared to the whole disk density. And the numbers that you end up with are at the same ballpark as the number density that you obtain in the spherical shell case. You can get a similar number just if you look at the stellar population after formation from the observations, halo mass of 10 to the 11 and radius of 0.3 kpc give you a number density of stars in the right ballpark, probably reflecting the gas density before the stars were formed. So I concluded that density and metallicity for feedback-free starburst arises naturally, early enough, and in halos massive enough. This is the number density as a function of time. This is the two extreme cases of spherical shock and a disk. And you cross the feedback density or the cooling density at the redshift of order 10. So this really, the conditions are at redshift 10 and above, and masses above 10 to the 11. Now clusters and generations, which I warned you about. In the case of a shell, we're talking about Gibbs instability. The Gibbs mass is of order globular cluster, 10 to the 6 solar masses. And you need, for the fragmentation to occur here, to accumulate enough mass from the accretion of the gas through the halo, the 80 million years accretion rate. And this tells you that you have to wait until you accumulate on the order of billion solar mass in accreted gas before you have enough to have the Gibbs mass inside the Gibbs radius and get the fragmentation going. At that point, you make those stellar clusters, FFB, and you have to wait for another billion solar mass to come in, another roughly 10 million years to build it up. In the case of tubular instability, the clumps are the tubular clumps, and you have to make sure that Q is less than 1. Now, if you have no gas, then this is 0, no gas, and Q is very high. You have to wait until the accretion brings in, through streams, enough gas, again, about 10 to the 9 solar masses of gas, to make Q below 1, to make the fragmentation go, a burst of FFB clusters to form, and then you wait another 10 million years for another billion solar mass of gas to come in. In this case, the clumps are somewhat bigger than a globular cluster, but the generation is again containing about 1 billion solar masses. So one predicts this kind of star formation history, a burst of about 1,000 globular clusters forming FFB in a few million years, and then a generation of 10 million years waiting until the next burst comes in for the next generation, either in a shell or in a disk. In both cases, it's a very similar story. About 10 generations of 10 million years each, with a peak of a few million years, and a star formation rate on average, epsilon, star formation efficiency, times the accretion rate. Up. So, before I go to the observations, again, that's the picture. Here's a galaxy, sub-KPC scale, maybe 0.3, with 10,000 globular cluster-like objects that do many interesting things. Little gas, little dust, and many implications like black hole seed formation in these clusters. Globular clusters may form this way, so part of them, it may affect ionization, and so on. So the prediction is, in this plane of redshift and halo mass, that there is a threshold line above which you have feedback-free starburst, below which you don't. And it's about, at redshift 10, it's about 10 to the 11 solar mass. At redshift 15, it's about a few times 10 to the 9 solar mass halos. This line is 5 sigma peaks. So we are talking about 4 to 5 sigma peaks at all times. I started 5 minutes late. Now the things you may care about. So now we put this theory into prediction mode, and Giorgio is doing this work. So what we do is we assume that this epsilon, star formation efficiency, at a given redshift, say 9, is this purple line. It starts low, like what Peter Beruzzi proposes, but it reaches a maximum value of order unity, being really 1, or maybe as low as 0.2 or somewhere in between, higher than the 0.1 you expect at low redshift and low masses. So this is the input model, and I'm just going to use some examples. Now take seriously my theoretical predictions, don't take seriously my comparison to observations. I just do it for the fun. So this is the star formation history, the Madar plot. This is what we get from Peter Beruzzi, extrapolation. And this is what we get for our model with maximum efficiency of 1, and this is with 20%. So our model predicts something around here. Now some data in here. It seems to point out to about 20% efficiency at the maximum. But again, don't take it too seriously. At this point, many of you are going to work on this and give us the best result. Also remember that our lines are upper limits because we have not put in any dust attenuation yet. So this may lower some numbers down. Everybody likes luminosity functions. Redshift 9, 10, 12, 16. 3 choices of epsilon max, 1, 0.5, 0.2. Peter Beruzzi's line is the solid line with attenuation, the dashed line, and Aaron Young average prediction from semantic models is the dotted line that Aaron just showed us, representing many of the simulations in the same ballpark. You want the data? Again, so many data, and so many are coming in, some presented for the first time in this meeting. Well, look at redshift 12. Starts getting convincing that we need these higher values. Well, I can't really tell if it's 0.2 or 1 or in between. Again, remember attenuation may lower our curves a little bit. sensitive to short time scales, and the blue is what you expect from a UV, phi UV indicator, and the ratio between the two, you see it goes from unity to a small number here, can tell you whether you have this kind of periodicity or not, and what are the times for the width of the peak and the width of the generation. So that's possible to be done. And my last prediction is the fact of 21 centimeter. That's work done by a postdoc now in preparation. That's the power spectrum predicted as function of redshift. That's the standard model, the black. And the orange is the FFB model. You can see that above redshift 12, you see significant deviations as far as the Hera plus minus 1 sigma error bars are expected to be. So this is detectable, this kind of. Unfortunately, reionization, the integral is not going to be very different in the FFB scenario. So there are a few things we want still to add, and we want to perform proper simulations that will have the right feedback and resolution to really be able to reproduce this kind of behavior that we predict. At the moment, for the observers among you and the simulators, we predict and we can provide digital predictions for those curves that people are welcome to put in their new observational papers. So this is a list of observable predictions which are distinguishing this from different models. I just want to highlight the fact that it's not only a redshift threshold above which you have to be to get FFB, it's also a threshold in mass. You have to be massive for strong FFB behavior. That's a very strong prediction that is probably different from others in other models that try to explain this. And many, many other predictions which I won't go through. Let me go right at the conclusions. We expect feedback-free starbursts with high efficiency of star formation once the density is above this critical number and the surface density is above this critical number. This allows a free-fall collapse in the window of opportunity of 1 or 2 million years that feedback provides you with, as long as the metallicity is not too high. This leads to starbursts on a cooling time scale that's shorter than free-fall time. The clusters they form are self-shielded once they're massive enough, and there's a feeding by cold streams for these massive halos at high redshift. This is valid above redshift 10, at halo mass above the threshold, both in the case of a post-shock density in a shell or in the disks that form tunnel clumps, typically 10 generations of billion solar masses and bursting star formation history. Many observables, which I won't go into, and many implications, in particular for black hole seeding, global cluster formation, effect on realization, and you tell me, every day there's a new idea for what to do with this. And I think I'm done here. Thank you.
Thank you, Avishai. Great talk. Let's open it up for questions.
Avishai, you're always good for out-of-the-box thinking, and so I love it to listen to you. I had a question about this kind of density. You know, the typical surface densities of molecular clouds are of the same order, but they don't form stars with 100% efficiency. It's still an efficiency of a few percent. Wouldn't this contradict what you say? So shouldn't each molecular cloud in the Milky Way also efficiently form stars then?
Well, you have to worry about many caveats that I mentioned, in particular shielding against UV, shielding against supernova winds, and so on. I'm not sure that I'm sure that not all of these necessary conditions are valid in Milky Way things. They are valid by some coincidence, all of them, at this window of opportunity of high redshift and high density. Now, this is not thinking out of the box. It ends up as very much in the box theory. It's standard physics. This is the box. This is the new box.
Okay, I like the new box, the color of the new box. And in fact, I buy most of the physical arguments you have. However, I have a simple question. So if you have this star formation history that is made of 10 generations of bursts, and in each one you form about 10 to the 8, 10 to the 9 stars, those stars will enrich the gas with metals and dust. So the second burst will not satisfy, probably, this is a question asked, will not satisfy the FFP conditions anymore.
The same calculation that promised that we have shielding against the supernova wind is also shielding against contamination by metals from the old generation to the new generation. Okay? It's the same calculation. We simply computed the flux that comes in from all the previous generations, how it's going to affect the new clusters. It's not going to affect it if they're massive enough, and metals are not going to contaminate these new clusters until sometime later. So it's the same calculation that we have been done, which tells you that the metals are not going to be a problem.
Okay, one more quick question. We can get the next speaker to set up, please.
Thank you for the very nice talk. I think the idea that star formation efficiency can be high in these conditions is fundamentally correct, so I'm just going to quibble a bit more about the specifics. Why can't star formation efficiency also be high even after supernovae and winds have started? Because I've run simulations that run for 10 megayears, and as long as the surface density is high, it seems like the star formation efficiencies can still be high.
All the conditions working for you. You have to make sure that any feedback is not throwing out the gas. You have to make sure that supernovae don't throw out the gas. Still, everything has to be working together.
Thanks.
Right, let's thank Avishai again. We can continue talking.